Welcome to this set on electric current, resistance, and Ohm's law. 11 questions, one underlying theme, reading a circuit diagram and predicting its behavior without solving it numerically. Every question ahead makes use of one of 5 moves: series and parallel collapse, equipotential symmetry, wide delta equivalence, the ohmic versus non-ohmic distinction, and the single formula R equals rho L over. The trick is to spot which move belongs to the diagram before you reach for the calculator. The order of the questions is roughly the order in which the underlying tricks appear. Some questions ask you to find a single missing resistor. Some ask you to read an IV curve, some ask you to locate a fault in a cable. Each one highlights a different tool, and by the end of the set, all 5 moves will have appeared at least once. Before we touch the questions, let's lock down the vocabulary. We will use equivalent resistance to mean the single resistor that draws the same current from the same source as the original network. We will use equipotential points to mean nodes that sit at the same electric potential. A wire between them carries no current, so we are free to weld the points together or remove the wire entirely. An ohmic conductor is one whose current is always proportional to voltage, which shows up on an IV plot as a straight line through the origin. And a potential divider is just 2 impedances in series across a source, where the voltage across one of them is a fixed fraction of the source voltage. One rule of thumb you will hear over and over in the voiceovers: name the technique first, then compute. Reading the diagram correctly is half the answer, and arithmetic is only the bookkeeping step that follows. With that in mind, let's begin with the first question. Question 1 gives us 2 3-terminal networks, a Y on the left and a delta on the right, and asks what single resistor value on the delta would make the 2 networks interchangeable. The trick is wide delta equivalence. 2 such networks look identical to the outside world when the resistance between every pair of terminals is the same. We will write down the pair resistances for the Y, then set the corresponding delta pair resistance equal to the YS, and solve for R. Before you solve, take a good look at the diagrams. The Y has 3 resistors meeting at a center node, 200 ohms between A and the center, 300 ohms between B and the center, 600 ohms between C and the center. The delta on the right has 600 ohms directly between A and B, 18 ohms directly between B and C, and the unknown R between A and C. The 2 networks have to be interchangeable when looked at from the A, B, C terminals. But nothing is stated about what is connected to those terminals, so the equivalence must hold for any choice of external network. The principle here is simple to state. 2 3-terminal networks look identical to an external circuit when all 3 pair resistances match. That gives us 3 equations in 3 unknowns, but in this problem 2 of the delta resistors are already given, so a single match is enough. Step 1, look at the Y on the left. Each pair of terminals goes through the center node in series, with no other branches attached to the center. So RAB is the sum of the 2 arms A to center and center to B, that is 200 plus 300 equals 500 ohms. RAC is 200 plus 600 equals 800 ohms. RBC is 300 plus 600 equals 900 ohms. 3 numbers, each a simple series sum. Step 2, now compute the odd pair resistance on the delta. With terminal C left open so no current leaves through C looking in at A and B, we see 2 paths between them. The direct 600 ohm resistor, and the path going through A to C to be in series, that is R plus 18 ohms. Those 2 paths are in parallel, so R ob on the delta is 600 times R plus 18 divided by 600 plus R plus 18 which simplifies to 600, R plus 18 over R plus 24 Set that equal to the YS 500 ohms and cross-multiply. 5 times R plus 24 equals 6 times R plus 18 giving 5 R plus 12,000 equals 6 R plus 10,800. Solve R equals 1,200 ohms. Option 4, Step 3. As a sanity check, compute RAC on the delta with B open. The 2 paths are the direct R and the series 600 plus 18 equals 24 With R equals 1,200, that gives 24 times 1,200 divided by 36 which is exactly 800 ohms, matching the YS 800 ohm upside pair we computed earlier. The third pair matches automatically because both networks are fully determined by their 3 edge values. The trap is treating the delta as if it were a series chain. The 3 resistors form a triangle, not a line, so any pair resistance always involves one direct edge in parallel with the series sum of the other 2 edges. The Y, by contrast, has the center node doing all the work. Every pair goes through that single center. The transferable insight: in any problem where 2 3-terminal networks must be interchangeable, write the pair resistances of both and match them. With 3 given resistors per network, one matches enough and the other 2 fall out automatically. This same logic drives the Wheatstone-Bridge null condition, which you may meet again later in the course. Question 2 is one of the cleanest illustrations of why Ohm's law is a property of the device, not a universal law. We have 2 circuits sitting side by side, one with a resistor X, one with a torch bulb Y. We are given that at a tiny current of 2 milliamps, both devices drop 0.3 volts. Then we crank the current up to 40 milliamps, the bulb's filament begins to glow, and the question asks what the voltmeters now read. Before you look at the options, think about what is happening physically. The resistor X is made of resistance wire and stays at room temperature throughout. The bulb Y is a filament that, at 40 milliamps, is hot enough to glow. Hot filament means a much higher resistance than the cold filament we measured at 2 milliamps. So the same current through a hotter resistor demands a bigger voltage drop. Now to the working. Step 1. Use the low current reading to calibrate. At I equals 2 mA and V equals 0.3 V, both devices have a cold resistance of 0.3 volts divided by 2 mA, which is 150 ohms. At this stage, we cannot tell the resistor and the bulb apart. They behave identically when cold. Step 2. Predict the ohmic resistor X at 40 mA because X obeys V equals IR at every current. The V to I ratio stays at 150 ohms. So Vx equals 40 mA times 150 ohms, which is 6 volts. This immediately rules out options 4 and 5, where Vx is given as 3 volts. Notice that the remaining options 1, 2, and 3 all give Vx equals 6V, so the choice between them rests entirely on Vy, the bulb's reading. Step 3. Predict the bulb at 40 mA. The filament is glowing, its temperature has risen, and its resistance has climbed well above 150 ohms. To push the same 40 mA through a higher resistance, the source must supply a higher voltage. In symbols, Vy is greater than Vx, which is greater than 6 volts. Only option 3, Vx equals 6V and Vy equals 9V, satisfies this. That implies the bulb's hot resistance is 9 volts divided by 40 mA, which is 225 ohms, 1.5 times its cold resistance. The trap to avoid is treating the bulb as ohmic. At low current, the filament is barely warm, so the bulb looks like a 150 ohm resistor. That misleads people into thinking the answer is option 2, where Vy equals Vx. The clue in the question is the word glows. Once the filament lights up, you know the temperature has moved and with it the resistance. This same distinction will return in the next question, where we look at IV curves directly and ask which of 4 graphs obeys Ohm's law. The visual fingerprint of an ohmic device is a straight line through the origin. Anything else signals non-ohmic behavior at that operating point. Question 3 steps back from a specific circuit to ask about Ohm's law in its purest form. Which IV curve actually obeys it? 4 graphs, labeled A through D, each plotting current I on the vertical axis against voltage V on the horizontal axis. The 4 graphs have visually similar features: straight lines, curves, intercepts, and the answer hinges on knowing exactly what Ohm's law demands. Before we read each graph, recall the form of Ohm's law. V equals IR for a passive conductor. Rearranged, I equals V divided by R, which is a straight line through the origin with slope 1 over R2 conditions. Then the line must be straight, R constant, and it must pass through the origin. V equals 0 implies I equals 0. Every deviation from these two conditions is a sign that the device is doing something non-ohmic. The principle in one breath. For a passive conductor, Ohm's law is V equals IR with R a constant. In IV coordinates, that becomes I equals 1/R times V, a straight line through the origin. The intercept has to be 0 because a passive resistor cannot produce current at 0 voltage. So the answer must come from a graph showing both a constant slope and a 0 I-intercept. The fingerprint figure makes that vivid. A clean straight line through O, with slope 1 over R, that is the only visual signature we are looking for. Now walk through the graphs. Graph A is a straight line that does pass through the origin. Slope is positive, intercept is 0. This is exactly I equals 1/R times V, which is Ohm's law, tick. Graph B is an upward curving line through the origin. So R is not constant here. As V increases, the slope grows, meaning the effective resistance is falling. That's a non-ohmic device whose conductance improves as it warms. A thermistor's cold to hot transition is the textbook example. Not Ohm's law. Graph C is a straight line, but the line sits above the V-axis. It has a positive I-intercept. A positive intercept means current flows even when V equals 0, which is impossible for a passive resistor. Something is delivering energy, not just dissipating it. not Ohm's law. Graph D is a horizontal line above the V-axis current independent of voltage. That is an ideal current source with infinite resistance and slope 0. Not a passive conductor, not Ohm's law. The most tempting trap is option 2, A and C, because both A and C are straight lines and people remember linear is good. But linearity is necessary, not sufficient. The line also has to pass through the origin. The pass-through origin requirement rules C out and locks the answer to A, the transferable insight. When you see an IV graph, look for two features at once. The slope is constant, R is constant, and the line passes through 0, a passive device. Either missing and you are looking at a non-ohmic component. We will use exactly this distinction again when a torch bulb's filament heats up during the next few questions. Question 4 is a potential divider with a twist. One arm is variable, and we are asked for the maximum voltage that can appear across a particular pair of terminals. The layout drawn from the source figure shows a source V feeding one fixed resistor R, then splitting into a parallel section. Branch 1 is a single R. Branch 2 is the variable resistor X in series with another fixed. The terminals X and Y sit across the variable resistor. That is what we are tapping. Before you compute, stop and think about which extreme maximizes the tap voltage. The voltage across any one branch in a divider is proportional to that branch's share of the total parallel section resistance. The variable resistor appears in branch 2 only. So pushing X up makes branch 2 the dominant branch by resistance, and most of the parallel section voltage lands across the whole of branch 2. That suggests X equals its maximum, R is our extreme. First, let's look at the principle. A potential divider shares voltage between two arms in proportion to their resistances. To maximize the voltage output, we push the variable resistor to its highest value. Step 1 is to locate terminals X and Y in the network. The source voltage V feeds a fixed series resistor R, which then connects to a parallel section. Branch 1 contains a single resistor R, while branch 2 contains the variable resistor X in series with another fixed resistor R. The terminals X and Y sit directly across the variable resistor. In step 2, to maximize the tapped voltage, we push X to its maximum value, which is R. Because series resistors share voltage in proportion to their resistance, a larger resistance X drops a larger share of the parallel section's voltage. Therefore, the maximum voltage Vxy occurs when X equals R. Step 2 continued. With X equals R, branch 2 has total resistance 2R. The two branches in parallel are R and 2R, so the parallel equivalent is R times 2R divided by R plus 2R, which is 2R over 3. Add the fixed series resistor R in front. The source sees R plus 2R over 3, which is 5R over 3. Source current I equals V divided by 5R/3 equals 3V divided by 5R. Step 3, find Vxy. The voltage across the parallel section equals I times R parallel, which is 3V over 5R times 2R over 3, simplifying to 2V over 5. Inside branch 2, the current is V parallel divided by 2R, which is 2V/5 divided by 2R, equal to V over 5R. The variable resistor X carries that branch current, so Vxy equals I branch 2 times X equals V over 5R times R, which is V over 5. The maximum tap voltage is V over 5, option 1. The trap here is a tempting one. Set X to 0 on the assumption that no resistance in the tap arm lets the full source voltage appear across XY. It doesn't. With X equals 0, the variable resistor carries no voltage drop at all, so Vxy equals 0. Worse, the rest of the source voltage is still being dropped by the fixed series resistor and the other branch. None of it lands across an arm of 0 resistance. The transferable insight. When a divider has one variable arm, the maximum tap voltage sits at one extreme of the variable, never in the middle. Read the topology first, set the variable to the extreme that maximizes the desired share, then apply the divider ratio directly. This general rule saves you from doing calculus on a problem that is really just an endpoint check. The three-panel figure shows the same divider at three positions of the wiper. The first two panels show the tap arm small. In the rightmost panel, the variable resistor has been pushed to its maximum, and the voltmeter reads V' equal to V over 5, the maximum extreme case we just computed by hand. Question 5 is a quiet but instructive question about how to define effective resistivity for a composite conductor. The setup: two wires of equal cross-sectional area A, one of length L and resistivity ρ1, the other of length 2L and resistivity ρ2, are joined end to end. The question asks what single ρ value would If plugged into the master formula R equals rho L over A with the composite's full length 3L and area A, reproduce the resistance of the joined pair. The catch is that the two segments have unequal lengths. The second one is twice as long as the first. So an effective rho cannot be a simple unweighted average of the two materials. It has to weight each material by its segment's length. That is the entire puzzle. The principle in one line. Effective resistivity is the rho that, fed into R equals rho L/A with the composite's overall length and area, gives back the composite's actual resistance. For two pieces in series, and this is what we have here, the individual resistances add. Step 1. Write each segment's resistance. Both segments share the same area. A segment 1 has rho equals rho 1L over A. Segment 2 has rho equals rho 2 times 2L over A, which is 2 rho 2L over A. Step 2. Add them in series. The current goes through one segment, then the other, no branching, so the two resistances add. R equals rho plus rho equals rho 1L over A plus 2 rho 2L over A, which combines to rho 1 plus 2 rho 2L over A. Step 3. Compare with the effective rho form. The composite has total length 3L, and the same area A. An effective rho would give R equals rho times 3L over A. Equate the two expressions, and the L over a factor cancels, leaving 3 rho equals rho 1 plus 2 rho 2. So rho equals rho 1 plus 2 rho 2/3. That is option 5. The trap is to reach for the simple average rho 1 plus rho 2/2. That would be correct only if both segments had equal length. Here the second segment is twice as long, so its resistivity contributes twice as much to the composite's effective rho. The length weighting in option 5 captures exactly that. The transferable insight. Anytime you join several conductors in series, and only in series, the composite's effective resistivity is a length-weighted average of the individual resistivities. Weight each rho I by its segment's length lay, sum those weighted resistivities, and divide by the total length. This same recipe works for any number of segments, not just two. We will revisit the underlying master formula R equals rho L/A in the next question, where we ask which physical changes actually move a metal wire's resistance. Question 6 invites us back to the master formula R equals rho L/A and asks which physical changes will move a metal wire's resistance upward. The three statements are: A. The wire is stretched to a longer length. B. The wire's temperature is increased. C. The wire is coiled into a solenoid. We have to decide for each one whether the resistance goes up. The most efficient way to handle this kind of multiple statement question is to anchor on the formula and ask, for each statement, which of the three knobs rho L/A has moved. If none of them has moved, the resistance is unchanged. If anyone has moved in the direction that increases R, that statement contributes to the answer. The principle, R equals rho L/A. The three knobs or rho depends on material and temperature. L depends on the wire's shape, and it depends on the wire's cross-section. Any physical change that does not move one of these knobs leaves R alone. Statement A. Stretching a wire. The wire's volume is conserved during stretching, so L times it is constant. If we stretch by a factor K, that is, the length becomes KL. Then the cross-section shrinks to a /K, substituting into R equals rho L/A. The new resistance is rho times KL divided by a /K equals K squared times rho L over A equals K squared R. Stretching by even a small factor raises R by its square. Statement A is in. Statement B. Heating a metal wire. Metals have a positive temperature coefficient. Heating the lattice increases the thermal agitation, which scatters conduction electrons more, which raises rho. For semiconductors, the trend is reversed. Heat liberates more charge carriers, lowering rho, but for a metal the answer is unambiguous. R goes up. Statement B is in. Statement C. Coiling into a solenoid. Coiling rearranges the wire's geometry, but the wire itself, its length, its cross-section, its resistivity is unchanged. R does not change. The thing coiling changes is inductance, but inductance only matters when the current is changing with time. For the steady DC measurements of this question, R is the same as it was. So the answer is A and B, only option 4. The trap is to pick all three because each statement sounds physically meaningful. Coiling does add an inductance, and a stretched wire does thin as well as lengthen, but the cross-section thinning effect of stretching is the very reason R rises so dramatically. The point is that it has two competing effects, L rises and A falls, and they reinforce each other, both pointing to R increasing. The transferable insight: name which knob is moving before you commit to an answer. L moves in statement A, rho moves in statement B, none of the three knobs moves in statement C. And that is why coiling does not change DC resistance. Question 7 is a wonderfully practical problem. We have an underground cable 4 kilometers long, made of 2 identical conductors running side by side. Somewhere along its length, the 2 conductors have been shorted together, perhaps by water ingress, perhaps by a digger's pickaxe. We don't know where. 2 resistance measurements are available: 30 ohms measured from end A to end B, the left side, and 70 ohms from end C to end D, the right side. The question asks how far the short sits from end A. The key insight is that each measurement probes a different segment of the cable. The short divides the cable into 2 pieces, and the 2 measurements give us 2 equations in 2 unknowns: the distance x and the cable's per kilometer resistance. The principle: a short between the 2 conductors at distance x from end A leaves a segment of length x on the A side with a short across it, and a segment of length 4 minus x on the C side that is intact. Each measurement of end-to-end resistance probes one segment at a time. Before any algebra, let us redraw the cable. The figure shows 2 parallel conductors, A above and B below, joined at both ends. Somewhere between A and C, the conductors are connected by a curved line representing the short. We ignore that curved segment because the 2 conductors run side by side and the short adds no measurable length. Step 1. Resistance of one segment. Each measurement spans both conductors. Current goes down one and back along the other. A segment of length L therefore contributes twice the single-wire resistance ρ times L over A. So R segment equals 2 ρ L over A equals K times L, where K equals 2 ρ over A is a constant for this cable. Resistance scales linearly with length. Step 2. 2 measurements, 2 equations. Let x be the distance from A to the short. The A to B measurement probes the shorted segment of length x, so 30 equals kx. The C to D measurement probes the intact segment of length 4 minus x, so 70 equals k times 4 minus x. 2 linear equations. Step 3. Eliminate k. Divide equation 2 by equation 1 to get 70/30, which is 7/3, equal to 4 minus x over x. Cross multiply. 7x equals 3 times 4 minus x equals 12 minus 3x. So 10x equals 12 and x equals 1.2 km. Option 2. The trap is to read the figure literally and worry about the bent, return segment shown between the 2 conductors. That curve is just an artist's stylized wire. Physically, the 2 cables run parallel and the short adds no length worth accounting for. Always check whether a curved path in the diagram is decorative or an actual resistive element. The transferable insight. End-to-end resistance measurements locate a fault precisely because each end probes a different segment of the broken cable. The ratio of the 2 readings is the ratio of the 2 segment lengths, and that ratio is enough to find the fault position without knowing the cable's per kilometer resistance. This is a very common technique in fault finding on long cables and telephone lines. Question 8 is the question that scares everyone the first time they see it. A tangle of resistors between terminals A and B, with branches going sideways, parallel pairs, and a center chain. We are asked for the equivalent resistance between A and B before you start adding things up. Take a step back. Even messy networks obey a rule: they collapse one clean pair at a time. If at this point you cannot see a clean series pair or a clean parallel pair anywhere in the diagram, you have not yet looked at it the right way. The trick is to find a single pair that is unambiguously series or unambiguously parallel. Combine just that pair, redraw the simpler diagram, and repeat. The principle is the entire method. Complex networks collapse one pair at a time. At each step, find a clean series pair, same current, no branching node between them, or a clean parallel pair, same voltage across both ends. Combine that pair, redraw, and repeat until you are left with one resistor. The arithmetic in each step is trivial. The difficulty is choosing which pair to collapse next. The 6-panel figure from the source walks through the simplification in stages. Each panel merges one clean pair and redraws the resulting network. Panel 1 is the original network. Panels 2 through 5 collapse one pair each. Panel 6 shows the final result, a single resistor of 7R/12 between A and B. Step by step for this network. Step 1. Each horizontal branch on the left and right contains 2 R resistors in parallel, giving R/2 per branch. 2 such branches in series give R/2 plus R/2 equals R per side. Step 2. The center branch has 2 R resistors in series, giving 2 R down the middle. Step 3. Reduce the rightmost chain, which has an additional series resistor on top of the already collapsed branches. The exact value depends on the precise node connections in the figure. The source's panel diagram carries out that intermediate collapse. Step 4. The remaining branches combine in parallel between A and B. The arithmetic shown in the source's 6-step diagram yields R eq equals 7R/12. That is option 3. The trap is trying to combine the whole network in one move. Complex networks resist that the steps have to be one clean pair at a time. Resist diagonals and three-way merges. If a step isn't an obvious series or parallel pair, look for a different pair first. The transferable insight. Treat the network as a recursive structure. At each step, find one clean pair, combine it, redraw, and repeat. When no clean pair exists, look for an equipotential by symmetry or for a Wheatstone bridge simplification. Those are the next moves beyond plain series/parallel. The arithmetic is bookkeeping. The judgment is in choosing which pair to collapse next, and that judgment comes from reading the diagram node by node. The next question is a perfect illustration of the symmetry shortcut. Question 9. The skeleton network is the cleanest illustration of an idea we have been building toward. Symmetry collapses networks for free. A square skeleton has terminals A and B on opposite corners. Each side of the square is a 1 ohm resistor. The question asks for the equivalent resistance between A and B, and the correct option is 5/6 of an ohm. Without the symmetry trick, this would mean solving a 4-resistor square problem by writing out loop and node equations. With the trick, it is 3 visual steps followed by a single line of arithmetic. The punchline is that the answer 5/6 of an ohm comes from welding together points that are at the same potential by symmetry, then collapsing the resulting series chain. The first setup step is to recognize which network the square skeleton actually maps to. The source's work note is explicit. The square skeleton's solution is identical to the equivalent resistance between A and G in example 2, which is a richer rectangular grid. 2 vertical branches, each with 3 resistors in series, joined by horizontal connectors and 2 diagonals. The symmetry trick works on the same skeleton either way, but the rectangular layout makes the diagonal axis of symmetry easier to see than on a 4-corner square. The second setup step is to draw the axis of symmetry and identify the equipotentials on it. For the rectangular grid between A and G, the dashed diagonal from A to G is the mirror line. By symmetry, points D, E, and the upper corner sit at exactly the same potential as their mirror twins across the diagonal. Those points become the equipotentials we weld together. This is the visual payoff of the symmetry approach. Once you have marked the diagonal and the equipotentials on it, the rest of the problem becomes mechanical. Returning to the square skeleton from the original question, the diagonal from A to B is the axis of symmetry. By the same logic we just applied to the rectangular grid, 3 points in the square sit at the same potential. The midpoint of the top side, which we call M1, the midpoint of the bottom side, M2, and the center of the square, M3. Each of these lies on the diagonal axis, and each is the average of its 2 end potentials. The original diagram is shown again, so you can see how the points map onto the square. The principle: 2 points that sit at the same electric potential are connected by a wire that carries no current. We can therefore either remove that wire or weld the 2 points together. Both operations leave every other current in the circuit unchanged. Step 1. Identify the axis of symmetry. Terminals A and B are on opposite corners of the square, so the network is mirror symmetric about the diagonal line connecting A and B. Every point on this axis is at the same potential as its mirror image across the line. Step 2. Find the equipotentials. The midpoint of any resistor that crosses the axis sits at exactly the average of its 2 end potentials. When both ends are symmetric about the axis, the midpoint is at the axis potential itself. Those midpoints, M1, M2, and the center M3, are the equipotentials we weld together. Slides 27 through 29 walk through the visual identification step by step. Step 3. Weld the equipotentials to the central node. This either removes a resistor entirely because no current flowed through it anyway, or combines 2 segments into a single branch. Either way, the weld is free. Step 4. Collapse the resulting network. The source's worked example for the AG case, shown here as a 4-panel figure, walks through exactly this collapse. Panel 1 is the welded network. Panel 2 shows the equivalent series branches. Panel 3 reduces them to a single 5/3 ohm resistor between A and G. Panel 4 shows the same branches as a series chain of 2/3, 2/6, 2/3 of an ohm. That figure was generated for the 2 ohm resistors of example 2. For our 1 ohm skeleton, the same pattern gives 1/3, 1/6, 1/3 of an ohm. Adding them in series. 1/3 plus 1/6 plus 1/3 equals 2 plus 1 plus 2 over 6, giving 5/6 of an ohm. That is option 4. The trap is to brute force the 4-resistor square by writing out all the loop and node equations. That works, but it is 10 lines and easy to error. The symmetry method gets the same answer in 3 visual steps plus 1 line of arithmetic. A mental image helps to remember why this works. Picture the current entering at A and leaving at B by symmetry. Exactly as much current flows along the top half as along the bottom half. Wherever those two halves meet in the middle, the currents cancel. That point is at the source midpoint potential, and any wire leading to it carries no current. Welding M1, M2, and M3 together is just acknowledging that null point in the network. The transferable insight. The same symmetry trick generalizes to almost any regular polygon resistor network. Find the axis, mark the equipotentials, weld them, then collapse. The sources example 1 square with diagonals and example 2 rectangular grid work the same way. Once the axis is named, the rest is mechanical. Connection to the next question. The very next slide set, question 10, uses the identical 3-branch decomposition. 12 equal resistors arranged between A and B collapse via the same equipotential weld into a top branch of R over 3, a middle branch of R over 6, and a bottom branch of R over 3, all in series. The skeleton here is the simplest case where the trick appears. Question 10 is the same trick applied to a richer layout. Question 10 doubles down on the symmetry trick we used in the previous question. 12 equal resistors, each of resistance R, are arranged in a layout between terminals A and B. We are asked for the equivalent resistance between A and B. The options include 5R over 6. Exactly the answer we found for the square skeleton earlier, which is a hint that the symmetry method is the right path here. Before you start reading out the network, take a step back. 12 individual resistors between 2 terminals is rarely 12 independent parallel paths. The layout symmetry guarantees that many of the intermediate nodes are at the same potential, and welding those nodes collapses the tangle into something you can collapse mechanically with series and parallel rules. The principle, 12 equal resistors between 2 terminals, is rarely 12 independent paths. The layout symmetry places many intermediate nodes at the same potential. Weld them and the network collapses to a handful of series parallel pieces. Step 1. Identify the equipotentials. The layout has left-right and top-bottom symmetry, so 3 specific points labeled X, Y, Z all sit at exactly the same potential. Weld them into a single node. The 4 crosspoints of B, C, D are each at their own distinct potential, but the 4 of them pair off as equipotential pairs that join the welded branches. The 4-panel figure walks through the simplification visually. Panel 1 is the original 12-resistor layout. Panel 2 marks the branches X, Y, and Z, and the 4 crosspoints of B, C, D. Panel 3 collapses each welded branch into a single fractional resistor. Panel 4 reduces everything to a single 5R over 6 resistor between A and B. Step 2. Reduce each welded branch with X, Y, Z fused. The top branch 3R resistors now in parallel after the welds reduces to R over 3. The middle branch 6R resistors in parallel after the welds reduces to R over 6. The bottom branch another 3R in parallel reduces to R over 3 as well. So between A and B we have 3 resistors, R over 3, R over 6, and R over 3 joined in series. The mental shortcut. Don't try to read the entire 12-resistor layout at once. Find the symmetries, weld them, and the network reveals itself as a clean series chain of 3 resistors, each of which has a parallel substructure that reduces by inspection. Step 3. Series combination. Rec equals R/3 plus R/6 plus R/3. Bring to a common denominator of 6, 2R over 6 plus R over 6 plus 2R over 6 giving 5R over 6. That is option 4. The trap is to treat the network as 12 independent parallel paths and compute Rec equals R over 12. That arithmetic comes out neatly, but it is wrong because the resistors are not all in parallel. Many of them are in series within a branch before the branches join. The symmetry collapse is what reveals the actual structure as 3 series resistors, not 12 parallel ones. The transferable insight. For any layout with multiple identical branches between 2 terminals, find the equipotential nodes first. The number of distinct potentials is almost always much smaller than the number of nodes, and each equipotential weld turns a tangle of crossings into a clean series parallel chain. The arithmetic then becomes bookkeeping. We will use the same source-to-equivalent resistance template in the next question, where a single source drives a partly series, partly parallel network, and we want the voltage across one internal subsection. Question 11 starts with a 150-volt source between terminals P and Q, and asks for the potential difference across a specific subsection, points R and S inside the network. The diagram shows a 10-ohm resistor feeding a parallel section. One branch of the parallel section is a 10-ohm resistor alone. The other branch is a pair of 5-ohm resistors in series. R and S sit on the lower branch. Notice that the question is asking about part of a parallel branch, not the whole branch. That detail decides whether the answer is 50 volts or 25 volts. The structure of the network forces a specific path through Ohm's law, and we will walk that path in order. The principal two resistor rules drive this whole problem. The same current flows through series resistors, so the voltage across each series piece is proportional to its resistance. The same voltage appears across parallel branches, so the current in each branch is inversely proportional to that branch's resistance. Combining the two rules gives the voltage across any subpiece. Step 1. Find the equivalent resistance of the parallel section. Branch 1 is a single 10-ohm resistor. Branch 2 is two 5-ohm resistors in series, total 10 ohms. Two equal 10-ohm branches in parallel give R parallel equals 10 times 10 over 20 equals 5 ohms. Step 2. Find the total resistance seen by the source. A 10-ohm series resistor sits in front of the parallel section. RPQ equals 10 plus 5 equals 15 ohms. The redrawn figure marks the entry and exit of the parallel section. Call them X and Y sitting between the 10-ohm series resistor in front and the parallel branches behind. That labeling makes the working that follows easier to read. Step 3. Source current and voltage across the parallel section. With VPQ equals 150 V and RPQ equals 15 ohms, I equals V slash R equals 150 slash 15 equals 10 amperes. The voltage across the parallel section is VXY equals I times R parallel, which is 10 times 5 equal to 50 volts. Step 4. Voltage across one 5-ohm resistor. The branch with the two 5-ohm resistors in series carries I branch equals VXY over 5 plus 5, which is 50 over 10, equal to 5 amperes. Each 5-ohm resistor drops V equals I branch times 5, which is 5 times 5, equal to 25 volts. R and S span one of these 5-ohm resistors, so VRS equals 25 volts. Option 1. The trap is to read the answer as 50 volts because VXY was 50 volts. The question asks about R and S specifically terminals inside one branch of the parallel section, not across the whole parallel section. Conflating the parallel section voltage with the subsection voltage costs the easy mark. The transferable insight. When a question gives a source voltage and asks about a subsection, work inward in this order: source voltage, equivalent resistance, source current, voltage across the relevant subblock. Each step is a single Ohm's law application. The structure of the network tells you which series and parallel rule to apply next. The 25-volt answer is half of the parallel section voltage because R and S happen to span one of the two equal 5-ohm resistors in their branch. The recap that follows ties together all 11 questions, 5 recurring moves, 5 recurring traps, and a short interleaving plan for revision. 3 principles run through all 11 questions and they bind the set together, worth memorizing in this exact form. Principle 1. Ohm's law is a property of the device, not a universal rule. A straight line through the origin on an IV plot is the visual signature of an ohmic conductor. Anything else is non-ohmic. The incandescent filament in QTWO is the canonical example. Same current requires a larger voltage drop once the filament glows because the resistance has moved with temperature. Principle 2. Resistance depends on 3 knobs rho L A. The single formula R equals rho L slash A governs Q7's stretched cable, Q6's heated wire, Q5's composite wire, and any other. What happens to R when X changes? Question. Each knob moves R in its own direction, and the only way to answer confidently is to name which knob is moving. Principle 3. Network reduction is a search for simplicity. 3 moves in order of preference. Series and parallel collapse when a clean pair exists. That is how Cone, K11, Q10, Kate, and Q4 all start. Equipotential symmetry when the network is balanced. Q9 is the pure case, and Q10 and Kate also exploit it once pairs are welded. Wide delta transformation when the network has 3 terminals and no other symmetry to exploit. Cone uses it to match a given delta to a Y. 5 traps showed up across the 11 questions, worth recognizing on first read so they don't cost you marks. Trap 1, reading the diagram's bent return path as a real resistor. In Q7, the cable loops back between the 2 conductors at the short, but the bent path has negligible length. Only the segments along the cable contribute to the resistance. Trap 2, treating the bulb as ohmic because its cold resistance matches the resistors. Qt separates cold, where the bulb looks ohmic-ish, from hot, where it is very non-ohmic. The high current reading is what forces the distinction. Trap 3, forgetting the order of operations on a divider. Q4's source resistor eats most of the source voltage. Only the remaining fraction is available to be tapped across the parallel section. Trap 4, computing the divider ratio naively when the source side has its own series resistance. Reduce the network first, then apply the divider rule to the remaining series arms. Trap 5, stopping the symmetry collapse too early. Once you have welded the equipotentials, the resulting network is still rarely trivial. Keep collapsing clean pairs until a single resistor remains. 4 questions to reattempt from memory. They cover the most reusable tricks. Q9, symmetry collapse. Without looking, sketch a square with terminals on opposite corners and derive the equivalent resistance using equipotentials. The axis trick is the most reusable move in the whole set. Kelvin, subsection voltage. This is the source to equivalent to current to subblock template that recurs in every multi-loop problem. Trace each step, apply Ohm's law once, and you will land on the right voltage. Q6, the 3 knobs. Memorize R equals rho L/A and the sign of each knob's contribution. The subtle one is stretching a wire. L goes up, A goes down, and R goes up by K squared. Volume conservation is the hidden constraint. Qt ohmic versus non-ohmic. Rederive the bulb's higher voltage drop from the principle that a hot filament has larger resistance and therefore demands a larger voltage at the same current. Interleaving plan for revision. The 11 questions cluster into 3 groups.